first time your large language model fails in production, it looks like confidence. It provides a clean answer, professional tone, and a wrong conclusion. Users trust these formatted outputs. Because the syntax is correct, they deploy the text, allowing silent code defects and fabricated policies to enter mission-critical workflows. This trust hides a difficult reality for developers. Engineering teams currently spend more time debugging AI hallucinations than they spend writing first principles code. Many teams are shipping raw, probabilistic statistical models as if they were deterministic products. Confident lies represent a failure in the system design surrounding the model. The standard approach treats the model as a standalone feature, controlled entirely by tweaking the text of the prompt. Prompt engineering cannot override probability. Under a live operational load, a system that relies on statistical guessing for exact precision eventually breaks down. LLMs function as infrastructure, not plugins. They require surrounding logic nodes, retrieval, tool execution, and validation to enforce strict operational boundaries. Production reliability comes from building a systemic reliability layer around the model rather than tweaking syntax. We can diagnose these failures through forensic textual analysis of real-world Wikipedia edits. LLMs are statistical algorithms. Their only function is to infer the most likely next token based on the patterns in their training material. This results in a mathematical regression to the mean. Because specific, unusual facts are statistically rare, the model smooths them into generic statements that apply to the widest variety of cases. When this happens, a precise description, like inventor of the first train coupling device, morphs into an exaggerated common denominator, a revolutionary titan of industry. In production outputs, this manifests as undue emphasis on a subject's legacy or importance, replacing rare facts with common puffery. This regression is an inescapable consequence of the model's weights. Prompt engineering cannot correct it permanently, because the underlying statistical distribution remains the same. Asking an unbounded probabilistic model for high precision will inevitably result in exaggerated generic output. This lack of specific knowledge forces the model to rely on linguistic crutches, tells that emerge across every subject it touches. We see an unnatural density of specific vocabulary in professional outputs. Words like delve, pivotal, and tapestry appear with a frequency that doesn't exist in human-only writing. The model also simulates balanced analysis using negative parallelisms, structures that claim a topic is not just X, but Y. The system hits a breaking point when it reaches the edge of its training data or formatting constraints. When the model lacks a fact to fulfill a prompt, it hallucinates structure. It generates academic citations complete with volume and issue numbers that have no basis in reality. This leads to markdown bleed, where the hidden instructions given to the model by the developer clash with the user's environment. You find raw formatting tags, JSON placeholders, and internal URL tracking parameters. These forensic tells show that the model cannot ground itself. The prompt is an insufficient abstraction for reliability. Fixing this requires an architecture designed to contain the model's unpredictable tendencies. In a production environment, the LLM must operate as a single probabilistic node within a deterministic infrastructure. A tiered router intercepts every query, deciding whether to escalate it. The RAG pipeline then bridges the knowledge gap. RAG replaces the model's internal guessing with verifiable data. It retrieves specific information from an external repository and forces the model to use it as the only source of truth. For operations like math or data lookups, the system uses tool calling, handing off deterministic tasks that language models cannot execute reliably on their own. Finally, schema validation enforces strict formatting rules, stripping out markdown bleed and errors before the data is delivered. This reliability layer separates fragile prototypes from enterprise-grade products. Engineering leadership must shift its focus. The goal isn't guaranteeing AI capability, but guaranteeing AI reliability. Rescuing a failing deployment requires an immediate, structured response. This is the 48-hour correction loop, a protocol designed to replace intuition with measurement. First, isolate a single failing workflow and extract a 50-query evaluation set from your actual usage logs. Next, define a strict scoring rubric for the outputs you expect. Benchmark your current system against the new architectural layer. Measure the result. You define success strictly by the error rate, latency, and the cost per interaction. The mandate for the team is clear. Spend your time fixing the system, not the prompt. Recovering an AI strategy requires engineering evaluation, not endless sessions of prompt tweaking. This shift in ML engineering mirrors the transition that happened with APIs and distributed systems. In any mature technology, discipline eventually replaces experimentation. The winning teams in enterprise AI will not be the ones simply holding the most capable base models. Victory goes to the teams that build the most predictable, guarded systems around those models. AI confidence is a statistical illusion. Reliability is an engineered choice.